Production of chitosan-based composite film reinforced with lignin-rich lignocellulose nanofibers from rice husk. Introduction. Rice husk, the hard-packed layer that envelops the inner grain of rice, constitute approximately 20 to 25% of the entire rice structure. Rice husks also contain useful components, including cellulose, hemicellulose, lignin, and silica. Nevertheless, the utilization of rice husks has been relatively limited primarily for feed sources or biochemical production. Lignocellulose, such as rice husk, is the most abundant substrate. It also holds great promise as a valuable resource in biorefinery applications. Nano-microfiber cellulose, a promising alternative material from the lignocellulose structure, has shown remarkable properties including biodegradability, high surface area, excellent mechanical strength, flexibility, mixability, and high elasticity. However, the production of lignin-containing nanofibrillated cellulose involves the inclusion of portions of hemicellulose and lignin, resulting in higher production efficiency and lower energy consumption. The utilization of lignocellulose nanofibers is an attractive option for modifying the surface properties of MFCs without an additional chemical-driven modification process. Compared with N above MFC, LCNF can be obtained using more environmentally friendly process while maintaining the properties of lignin and N above MFC, such as high thermal stability, hydrophobicity, and low polarity. Previous articles have confirmed the positive effect of adding N above MFCs as a reinforcing agent of chitosan films. For instance, Fernandez et al. Reported that the composite of chitosan NFC exhibits superior dispersion in their matrix and homogeneous flexible better thermomechanical properties. Nevertheless, because of the highly hydrophilic nature, additional hydrophobicity might be required during the preparation of chitosan-based composites. The presence of hydrophobic lignin in LCNF might be an economical and attractive option for reducing the water absorption of composites and improving the thermal and mechanical barrier properties of polymers. Material methods: rice husk and its compositional analysis. Dried and milled rice husk were obtained from Sarumi Filler, Korea, and their compositions were analyzed according to the laboratory analytical procedures of the National Renewable Energy Laboratory. Sugar were quantified using high-performance liquid chromatography equipped with an index detector and a Chodex column. Sugar derivatives, including alcohols, aldehydes, and organic acid, were analyzed on an HPLC read equipped with an Aminex column. Chemical pretreatment, enzymatic hydrolysis, and fermentation. The rice husks were chemical pretreated with 1% sulfuric acid at 50% solids loading in a microwave digestion system at 190 grades with 5 to 60 minutes holding at 1800 watts. The pretreated slurry was filtered through microcloth to separate the solid and liquid fraction. Next, the solid fraction was washed with distilled water until the pH reached 7 to eliminate any residual sulfuric acid. Some portions were dried at 45 grades for 3 days for compositional analysis, and others were stored at 4 grades for further process. The rice husks were enzymatically hydrolyzed with 20 filter paper units of the commercial enzyme Salic CTEC2 per gram substrate. 10% of the solid were incubated in a sodium-assisted buffer for 48 hours at 50 grades and 250 revolutions per minute in a check-in incubator. The hydrolysates were filtered through microcloth to separate the solid and liquid fraction. The remaining solids were raised with distilled water before the resulting solid slurry was stored at 4 grades for LCNF production, and a portion was dried at 40 grades for 3 days for compositional analysis. The LCNF production and categorization. The morphological characteristics of the produced LCNF were examined by field emission scanning electron microscopy. A drop of the LCNF suspension was dried at RT for 12 hours on an aluminum foil and sputtered and coated with osmium after mounting on a substrate with carbon tape to enhance conductivity. Preparation and categorization of chitosan-based films. The chitosan LCNF composite films were produced by using the modified method of crucible union based on the solvent casting method. Previously, a 1% chitosan solution was prepared by dissolving chitosan in 1% acetic acid at 350 revolutions per minute for 4 hours at RT. An LCNF suspension was added to the completely dissolved chitosan solution at radius of 1 to 1, 1 to 3, and 1 to 9. And the mixture was vigorously stirred for 12 hours at 200 revolutions per minute. The mixture was tempered into a polystyrene dish and dried at ambient temperature. Statistical analysis. The significance of difference between data was determined using one-way analysis of variance with values of p being less than 0.05. Data were expressed as the mean plus less standard deviation of 3 independent experiments. Results and discussion. Effect of chemical pretreatment on rice husk. An acid catalyst was initially used to remove lignocellulose because of acid treatment of lignocellulose biomass at a high temperature. Generally causes complete hydrolysis of hemicellulose with partial digestion of cellulose. As expected, xylene was also not detected during the acid hydrolysis at various temperatures. Therefore, the different contents of lignin in the remaining solid were selected by adjusting pretreatment times at 190 grades. The rice husk was subjected to the acid pretreatment for 5, 20, and 60 minutes, with the 3 times point being designated as 5A, 20A, and 60A, respectively, at a fixed temperature of 190 grades with 1% sulfuric acid and 50% solid loading. Only after 5 minutes of pretreatment, 100 removal of xylene was achieved. The solubilized hemicellulose, the primary component in the hydroxylate obtained after pretreatment, could also be valuable as a prebiotic or for conversion into another chemical compound such as hydroxymethylfurfural, levonic acid, and ethanol. After 5 minutes of acid pretreatment, the rice husk preliminarily consists of 41.6% glucan and 36.7% lignin. As the pretreatment progressed from 5 to 60 minutes, the residual glucan content decreased to 24.1% as the lignin content increased to 57.0%. Considering the initial amount of glucan and lignin, the glucose recovery yields markedly decreased from 78.5% to 33.5%. However, the lignin solids were enriched after pretreatment. As a next step, the cellulose in the acid pretreatment rice husk was selected with 25 pu of cellulose per gram glucan for 48 hours at 50 grades. Consequently, the solubilization degree of glucose reached 62.18% with biomass pretreatment for 5 minutes, and 65.38% with 20 AL, in contrast to a maximum of 8.32 from the untreated rice husk control. However, the solubilization degree of glucose, for example, 60 IL, significant decrease, probably due to the reduction in enzymatic digestibility under the extended acid conditions. The high proportion of lignin in samples, 60 AS, might also negatively affect enzyme activities or accessibilities of pretreated solids through lignin enzyme interactions. Overall, the glucan content in rice husks significantly reduced from 30.89% to a minimum of 9.07% after both acid pretreatment and enzymatic hydrolysis, and the lignin content significantly increased from 26.24% to a maximum of 66.76%. This change in the proportion of structural components was subsequently investigated for their compatibility with LCNF. Figure 1. Composition of untreated and pretreated rice husks in a solid fraction and liquid fraction, and composition of solids obtained after enzymatic hydrolysis, and D. Enzymatic digestibility with 25 ppus of enzymatic glucan for 48 hours at 50 rates. In figure A, we can see the composition of the rice husk with the three experiments of 5, 20, and 60 minutes. We can see how the glucan is decreasing and the lignin is increasing. In figure B, we can see something similar, but in this case with a liquid fraction, seeing how glucose varies the most between the experiments. In figure C, is very similar to figure A, but with a difference that is after enzymatic hydrolysis. In figure D, we see the percentage of enzymatic digestibility depending on the time of the experiment. The LCNF production from lignin-rich husks and its characterization. The three rice husk samples resulting after pretreatment and enzymatic hydrolysis were evaluated using a high-speed blender to enhance the surface internetwork properties and stabilities of LCNF, which were evaluated using sedimentation tests. The LCNF produced using 5IS, 20IS, and 60IS samples were designed as LCNF5, LCNF20, and LCNF60, respectively. The sedimentation rate also considerably increased with the initial treatment, but the extent of increased differences according to the pretreatment time. Figure 2. Effect of different grading times of sedimentation of lignocellulose nanofibers from pretreated and enzymatic hydrolyzed rice husk. In figure A, we have the graphic representation of the sedimentation ratio of the three experiments with 5 different times. In figure B, we have the transmittance of the three experiments. In figure C, D, and E are the images of the three experiments taken with an electron microscope. Preparation of chitosan-based LCNF films and their characterization. With 3 kV of accelerating voltage, the electron beam rendered the pure chitosan film unstable and induced surface cracks. The chitosan LCNF5 composite films with content of the range of 0 to 50% exhibit good dispersion of LCNF in the chitosan matrix. Moreover, the surface roughness of the films increases with an increase in the LCNF content. All LCNF particles, including LCNF5, LCNF20, and LCNF60, were well dispersed through the chitosan matrix and covered the surface. Furthermore, the above-mentioned instability of the 100 chitosan film caused by the irradiation treatment improved with the addition of LCNF, and no cracks were observed after extended beam irradiation times during measurement. Optical and mechanical properties of chitosan-based LCNF films. As a barrier to UV and visible light, optical properties comprise one of the most important key factors for packaging materials. In particular, in the food sector, UV light catalyzes oxidation and chemical reaction, which is the factor that decreases the quality of food. The optical properties of chitosan-based LCNF composite films were evaluated using an UV-based spectrophotometer, where the transmittance values at 300 and 350 nanometers representing the UV light region, and the values from 450 and 550 and 650 nanometers represent the visible light region. At a mixing ratio of 1:1, the chitosan LCNF composite films demonstrate high UV blocking capacity. Moreover, with an increase in the lignin content, the film color becomes darker, resulting in a stronger blocking effect of UV and visible light. According to the opacity of the composite films increases from 66.62% to 554.34%, with an increase in the pretreatment time, with the opacity being 52 to 0.25 times higher for chitosan LCNF 60 than for chitosan alone. Compared with pure chitosan films, LCNF incorporated films can be a protective option for food deterioration. The desired opacity can be achieved by controlling the pretreatment time and adjusting the mixing ratio. The incorporation of LCNF resulted in a noticeable elevation in Young's modulus for all composite films when compared to the pure chitosan film. Young's modulus serves as an indicator of film rigidity. This enhancement is described as the inherited characteristics of LCNF on the robust bonds established between chitosan and LCNF. However, at higher fuel loading, the lack of uniform dispersion and aggregation of lignin could result in uneven stress transfer between lignin and the matrix polymer. Consequently, an appropriate amount of LCNF input is required compared with the solvent. Figure 3. The same images of chitosan LCNF film. A. Pure chitosan film. B. Chitosan LCNF 5 9:1 film. C. Chitosan LCNF 3:1. D. Chitosan LCNF 5 1:1. E. Chitosan LCNF 20, and if F. LCNF 60 1:1. Table 1. In this table we have the transmittance of the two experiments. Transmittance is the magnitude of the light that passes through a body. Therefore, the greater the transmittance, the less opacity. As we can see, LCNF 60 has the more opacity. In the next slide, we're going to see a figure of chitosan in LCNF 60, and we see why is so opacity. Figure 4. In figures A and B, we have the transmittance of the experiment, with the difference that in figure B, chemical pretreatments were used. In figure C, we can observe the difference between the experiments and their color, explaining the transmittance. As we can see, chitosan LCNF 60 is almost black, so light won't pass through it easily. Figure 5. Tensile strength being A, B. Elongation at break, and C. Young modulus of chitosan composite films. The Young modulus is in essence the stiffness of a material. In other words, it's how easily it's bended or stretched. So LCNF 20 is the most to be bended or stretched. Figure 6. Ethanol production capacity of hydrolyze recovered from enzymatic hydrolysis after pretreatment. In the next slide, we want to explain this image, but we have to remember that 60 minutes has the most production of ethanol. Ethanol production using solvative fraction obtained after enzymatic hydrolysis. As a further study of LCNF production using residual solids obtained from enzymatic hydrolysis, the glucose solution in the liquor fraction obtained after hydrolysis were used as substrate for ethanol fermentation to demonstrate the feasibility of using rice husks as a raw material in the biorefining industry. The maximum ethanol production from rice husk was 5.07 grams per liter per liter from 60 IL after 14 hours, which revealed that the theoretical maximum ethanol yield could be 111.66% based on the amount of glucose consumed. High concentration of glucose could affect glucose consumption because high concentration in the fermentation media can cause hyperosmotic stress on the cells. The final product yields could be enhanced using metabolic improved organisms that might be tolerant to various inhibitory compounds including aldehydes and organic acids. Figure 7. Mass balance of overall process using S-Saccharomyces. Here in this image we have a resume of everything we have seen, starting with the rice husk, and after that we pass it through a chemical pretreatment that gives us a solid and a liquid product. The liquid product goes to a sugar fraction that have glucose and cellulose, but the solid product goes to an enzymatic hydrolyze that gives also a solid and a liquid product. The liquid product goes to a fermentation with 5% of Saccharomyces at 37 grades and the final product is ethanol. And the solid product goes to a mechanical treatment to produce LCNF. The flowchart shows the changes in the amount of the major compounds such as glucose, cellulose, and lignin. First, after chemical pretreatment, the solid and liquid fraction of containing 26.93 grams of glucose and 10.7 grams of sugar, respectively from 100 grams dry weight of rice husk, which subsequently saccharization and fermentation process 7.4 grams of ethanol was obtained. Either obtaining a high titer of ethanol production or a high amount of LCNF production is essential for maintaining sustainability and is necessary to perform further target process optimization. Conclusion. The LCNF containing both cellulose and lignin were successfully obtained from rice husk after acid pretreatment and enzymatic. Depending on the pretreatment condition, different concentrations of lignin were obtained from the rice husk, which resulted in altered hydrophobic properties of LCNF. The LCNF demonstrate high potential as an additive in chitosan-based composites and exhibit adjusted mechanical properties, which were primarily attributed to the proportion of lignin resulting from the different pretreatment times. That's everything for me. Thank you for your attention.